Okay, so the first thing that I noticed was when you report the result of statistical test, right? Try to, most of you just focused on the p-value aspect. Like, for example, you just focus on the p-value being small enough or not, right? Now, the p-value is calculated from the distribution of your test statistic, right? So basically, you have if you have a t-test, so you have your t-statistic has a t-distribution, right? With n-1 degrees of freedom. When you report the results, you do not have to say all these things like it has how many degrees of freedom and so on and so forth. And you also do not need to report the t-statistic value because it is actually clear from the p-value itself. Like, for example, if your t-statistic, this is, for example, your observed test statistic, right? So it is related to the p-value that you report because how your p-value looks like depends on the observed test statistic, right? And this observed test statistic changes depending on the degree of freedom, but your p-value remains from 0 to 1, right? So reporting the t-statistic is actually not useful. And in a consulting report, you don't actually want to include unnecessary things, okay? So you can report the p-value, but more importantly is that you should also report estimates of the population mean, because in your question you have two populations, right? And you have the sample mean for each of them. So you should actually report what these estimates are, just to give people some idea about the difference. So you might want to just say that, for example, you could say that the sample mean of population 1 was significantly higher. Okay, so here you put a bracket and you include, maybe you say mean equals to 25, for example, was significantly higher than the sample mean of population 2. This one you report, let's say this is 10. When you over here for significantly higher, you put a bracket here and write p-value equals to 0.001, for example. By writing the result like this, you let people know what is the estimated mean, right? One is 25, the other is 10. And the difference between 25 and 10 cannot be explained by chance. And the p-value here explains it clearly, all right? So this is the more concise way of writing. But I noticed a lot of you just focus on the p-value, checking whether it is less than 0.05 or not. And then that is actually a very old-fashioned way of doing things. And it's actually not very informative because you know that one is higher than the other. So by how much, right? Just knowing something is, the sample mean is significantly higher, it's not very informative. It could be significantly higher by 0.01, or it could be significantly higher by 10, or whatever value, right? So be sure to include these things, right? This information, because you have this information in the statistical output. And do not actually attach, when you write consulting reports, reporting a result, never actually attach your output inside the report, all right? You have to extract the information that's important from the output and write it in plain English, okay? Right, it's a lazy way of copying and pasting the output and letting your client scratch their heads, all right? So that's one thing. And let me see, over here, you might also insert 95% confidence interval for mean of population 1 minus mean of population 2. Then you can give the confidence interval, right? So that would also be very nice, okay? Okay, this is one thing. The second thing is about, it's about the necessity of doing transformation of data, right? So the logic is that, I think some of you didn't get the logic right. You said that the transformation is useful. Actually, the transformation in the old days, it is because your statistical test has to make certain sets of assumptions about the distribution of the data, right? So when those assumptions are not met, then in order for them to continue using the theoretical result, they have to do the transformation until it is actually valid. The test is actually valid for some kind of transformation of the data, right? For example, some kind of data, after you take log transformation, they become approximately normal. So they can then do the t-test, right, using the log transform data as input. It is actually fine with this, except that in the consulting setting, you are then dealing with the log transform data and not the original scale. So whether this is going to confuse your client or not is something that you need to consider, because taking log is actually easy for us. But you try to explain that to people who have an arts background or maybe some non-technical background. They will feel like some strange thing is going on. They'll start to wonder why you don't just do the statistical tests using the original data and you have to go through all this transformation. And if your answer is that you are doing this so that the assumptions of the test are fulfilled, so that you can use certain tests, I think they are not going to be very impressed, right? It's like the other way around, right? Instead of focusing on the data, you are focusing on the method, and you try to twist the data so that the method cannot be attacked, all right? So as far as possible, we don't want to, in a consulting setting, we try to keep the data at the original scale. So the idea is that if the result of transform data, okay, actually not result, conclusion, okay, is the same as the conclusion from original data, right? Then like for example, this one, your p-value is, let's say 0.2. But maybe like, okay, so then I give another example. I noticed something like this. This is 0.1. Let's say this one you got p-value is 0.3. Okay. In both cases, the p-value is actually too high. So both conclusions are the same. You have the same conclusion whether you transform or don't transform. So in this case, it is better to report to your client this result, okay? And of course, you can check it using permutation tests, right? The permutation test is just to as a kind of like a checker, all right? Of course, you can also use bootstrapping. But as far as possible, we try to only report this if necessary, all right? Only if they really make a difference, all right? Otherwise, you don't need to report that. For example, over here, if you do bootstrapping a permutation test, you get the p-value that is 0.21. It's fine, right? Okay, it is, although it is different from it, the conclusion is the same. You have to focus on the conclusion. I noticed that some students, they compare the p-value. All right, I noticed there is for some students, they look at this, they say that, oh, the original one is 0.3. When I use permutation test or bootstrapping, it drops to 0.2. There's a drop of 0.1. So yes, then I should use permutation test. Actually, that is not a logical. It cannot be. This is an incoherent argument because number one, p-values cannot be compared between tests. Okay, this is a basic problem that occurs very often. Students like to compare p-values between different statistical tests. They actually cannot be compared. All right, p-values can only be used with respect to that particular test itself. And if you have several different tests, all right, and they have different p-values, you can't say that the result of A is more significant. This is actually a very common mistake at the undergrad level. Like for example, you have p-values between maybe a few examples like this, right? Some students will, so these are different statistical tests, right, from the similar data, okay, transformation and whatever. And then students, when they see this, right, they like to say that, oh, this one is smaller than this, so this result is more significant than this result, and so on and so forth. Please do not do that. Remember, you cannot compare p-values, all right? There's no basis for comparison, okay? Remember this. You cannot compare p-values, yeah? In the same manner, let me clear this. In the same manner, you have your regression model, okay? In your regression model, you have the, especially in multiple linear regression. So in the regression model, so usually you will have, for example, these are your estimates, right? Let's say you have, okay, so you have some value here, and of course you have a p-value, right? To test whether the regression coefficients differ significantly from 0. And sometimes you might have something like this. Okay. Then of course here clearly you will say that this is the variable 1 is actually not significant, right? Because the p-value is too high. And then you will say that, oh, these three are significant, all right? Because the p-value is smaller than 0.05. Well, that is fine. But what you should not say is that variable 2 is more significant because its p-value is, variable 4, this one, is more significant because its p-value is smallest. You should never say such things. All right, whether a variable is, all variables when they are statistically significant, they are just important. You cannot compare their p-value. They are important for the model. That's all. There's no way you can actually tell which one is more important. Okay, by checking the p-values. All right, so they all influence the model. Okay, the response variable. So avoid saying things like the p-value when it is very small, then you use it to rank them. Okay, don't rank them. Okay. Right. So this is one of the basic things that I noticed as well. I think after that, I think the rest are quite okay. Right. So you can actually later refer to our upload the solution guide later, and you can actually check it against your own answers, and how to so when you compare against, of course I don't actually allocate any marks for style and all that, right? Because I know that this is your first time, but you can actually look at the way I actually present the result and actually use that as a model next time if you want to attempt to present analysis result for consultation report. Okay, so in this round I basically just award marks based on the correctness of the approach, all right, the analysis, more or less. Okay, I do not say focus too much on the presentation, right? And then one more thing is the following. In the first question, was about what was that? That question about cervical cancer, right? So in that question, I asked, how would you, if you have demographic variables, okay? How to use them? I think a lot of you just said, oh, you just use them in a regression model. Right, so I think that is very unclear. Okay, so what happened was you have age at first pregnancy, and this is the cervical cancer, the development of cervical cancer in later life, right? Okay, so then you found that, okay, so age at first pregnancy was significantly associated with cervical cancer development, right? So we found this very easily using the chi-square test. But this age at first pregnancy is basically just a proxy, right? It's a proxy variable. By itself, it is very difficult to imagine why having a child before 25 or more than 25 can actually have anything to do with cervical cancer. Right? So this age at first pregnancy is basically a very useful proxy variable. And from this proxy, we know that this proxy variable is associated with cervical cancer development. That's fine. So that means in this case, those that are below or equal to 25, they are at a higher risk, right? So the doctor, when they check the patients, right, they find it to be useful. But what is exactly the cause, right? So if you only have the data like this, if you only have age at first pregnancy and whether they got cervical cancer development or not, you can't say much other than that they have association. Okay, so you need to bring in other kind of demographic variables. So for example, in the original, if you only have these two variables, your data is going to look like this. So this will be your ID, right? This patient 1, 2, 3, 4, 5. Okay, in the Excel sheet, they will look like this. This one, you will have their age at first pregnancy. So some of them will be below equals to 25. This will be more than 25. This is okay. And so on and so forth, right? You can record that. And over here, you can record whether they have cervical cancer. This one is yes, no, no, yes, no, no, and so on, right? So if you have this data, you can make this table, right? Now this obviously is actually not the final answer, because your final answer is you are trying to find some causative factor, something that actually is likely to have some kind of be the real cause for cervical cancer, right? So you will collect additional variables such as income, right? You can when you interview the person, you can find income, right? You can collect other things like education level and number of sexual partners, okay, and so on and so forth, okay. There are many things, there are many other things you can collect, all right. So the idea is since this is significantly associated with cervical cancer, then it follows that if, for example, age at first pregnancy is significantly associated with the number of sex partners, all right, then we can actually consider this demographic variables context, right? Okay, if this is significantly associated and this proxy is also significantly associated with another of these demographic variable, this will become a candidate for discussion. All right, so you can actually use that to design further kinds of experiments. Okay, so the idea here is that you need to do some kind of correlation analysis. Okay, you can the straightforward one would be you do pairwise correlations, right? You can correlate with, try to find a correlation between in this case, since it's categorical, you might actually be doing different chi-square tests, right? Or you could also do modeling, which is okay. You can do modeling whereby you're modeling now your response variable is age at first pregnancy, all right? And then it's equal to this, your predictors are income, education level, number of sexual partners, etc., right? You use this model and then you can find out which one of these are significant, okay? And then this you will follow up for subject matter consideration, all right? So that is how you actually use the demographic variables that you collect, right? Because this one is actually closer to the, some of these demographic variables are the closer to the cause rather than this thing. This is definitely just a proxy, okay? Age at first pregnancy. So I think quite a lot of you have some idea about, okay, use the modeling approach, but you didn't explicitly explain how exactly you are going to do that, right? So you have to understand the linkage, right? This guy is linked to this cervical cancer. So it follows that any of this, if you set this as a response, any of these predictors that are linked to it can also link back to this cervical cancer, okay? So this is the idea, all right? Okay. So in fact, for this problem, right, I think the epidemiology is the study of the prevalence and cause of some disease. For cervical cancer, actually now is well known that YH at first pregnancy, right, if it is too early, it actually can increase the risk of cervical cancer. That's because the earlier somebody has sexual encounter, if they encounter someone who actually carries the human papilloma virus, HPV, then they actually live with the virus for a longer time. Okay, this virus, once it's in the genital area, it can actually insert its DNA into the DNA of the woman, and then cause over time it can cause mutations in the cells at the cervical region, and therefore it causes subsequent development of cervical cancer. And as a woman has more and more sexual partners, right, the chances of this woman getting infected by the human papilloma virus is actually very high. Okay, and if a woman is sexually active at an early age, chances are they usually get pregnant quite early. Okay, so that's why that is this association, right? Okay, the real cause is, and actually the real cause is still not there, because the number of sexual partners is still a proxy for carrying virus. Okay, carrying the human papilloma virus, and as the number of sexual partners increases, right, that means this person is promiscuous. The promiscuous people usually they will tend to have they tend to get cross-infected from one another. So that's how they actually discovered later that this human papilloma virus is responsible for cervical cancer development, and that's why now they have vaccines, right? They have vaccination programs for young girls, right? They vaccinate against the there are different strains for human papilloma virus, so they vaccinate against those that are thought to actually lead to subsequent increase the risk of developing cervical cancer, right? So that is actually quite well known now. Okay. So that, I think they also discovered that through statistical applications, right? Okay, so that's some comments that I wanted to make about the assignment 2. Okay, are there any questions from you?
Good evening, doctor.
Yeah.
There's actually a question about the permutation test. I've read about this permutation test. It's only applicable if your data, the group is interchangeable. How do I know whether, the group of my data is interchangeable?
The interchangeability condition is basically is an abstract condition. So for practical application, basically you are just saying that I know they use a term called interchangeability, right? So
yes.
so that concept is actually an abstract concept, and I think for practical application, when you do permutation tests under the null hypothesis, the population label is not important. when the population label is not important, therefore they are interchangeable. So that is the idea. And therefore
Does
you
that
can,
means it's applicable to I mean the common kind of data or the
yeah. So when it is interchangeable simply means that if the label is not important, so you can think of some data coming from population 1, 2, 3 or whatever, you can think of that as where it comes from as a label. Like think of some sticker, right? Sticking there is a label. Under the null hypothesis, you are saying that all these populations have the same mean. If that's the case, then the labels don't matter, right? Because they all have the same mean anyway. So that means once they are not important, your labels you can change between one population and the other, right? That means your population 1, I can get the label from population 2. Doesn't matter under the null hypothesis. So that's why it's called interchangeable.
Okay. Thank you.
All right. Are there any other questions? Okay, so if you don't have questions, I think you can continue with your discussion among yourself, and you can ask me questions during this until 9:30, right? You can just open your mic and alert me, okay? Actually, I'll just stop the recording, right? So that it doesn't drag until 9:30. But if you have any questions, just send me a flock alert, and then I will talk to you, okay? Okay, you have questions about the group assignment, right? So what's your question, Amy?
Hello, doctor. Can you hear me?
Yeah, I can.
Yeah, about our group assignment, because our group chose the first topic, and in the first topic, firstly we need to deal with the variance to I mean about our group assignment. I have two ideas, but I hope you can order me good suggestions, because we don't know how to choose which is better. The first idea, because we learn some models in this semester, and in our group assignment we need to choose a good model for I don't know how to describe. I mean, we should focus we already learned model, or we can choose.
Well, you can use any model that's reasonable, but for that data set, I think first thing is your predictors. You have your response variable is a categorical variable, right? Whether the credit rating is good or bad, right? So then if you want to use a modeling approach, of course, logistic regression is very natural, right?
Yeah.
And then the other thing is you have a mixture of continuous and categorical variables, okay?
Yeah.
So of course, in a very straightforward way, you could basically just build a logistic regression model and see what happens. The other that is very straightforward, right? But but that model, if you do that, there are some potential issues that might arise. For example, a lot of the variables there, they are actually correlated. So there might be issues about, okay, how about interactions, right? The moment you start to consider interactions and all that, you will start to get a lot of, variables, and then your model may actually be very complicated. So the other approach is you can actually, since you already learned how to use guide, right? You can actually try to use guide to see what happens. Okay, that is also one possible way.
Yeah.
Right.
Can I use a graph named AUC to show the which is the best model?
That is actually a model selection, right? So you may have several models, and
Yeah.
you want to, okay.
Yeah.
Then,
Before this step, I need to try different model and summary different model results in AUC graph.
yes, you can do that. So if you do that, that means you have to arbitrarily split. You have to randomly split your data into a training set and a test set, right? So
Yes.
in order to make that kind of assessment.
Yeah, can I send the graph to you in vlog?
Yeah, you can just show me, okay?
Okay, thank you.
There's another way to do this question. The other way is to build some kind of credit score for the customer, okay? So that means instead of you kind of like build a system where if the client's variable for certain variables equal to certain values, you will give it a score of you will give it a certain score. So it's like a scorecard. So then you give, you translate that into some kind of a score. That's also possible, right? Actually, this data set has been studied for quite a long time. So there might be a lot of possible ways to approach it. But generally, the main thing here is that as long as I'm not looking at a perfect. There's actually no so-called perfect model, and it's just different ways of approaching the problem. As long as I think you can actually come up with a model that is reasonable, and you can coherently support it with an argument. I think that's fine already. I'm not looking at what kind of performance, optimal performance, and all that kind of things, because those kind of things they may require some specialized knowledge that you learn in the data mining course or whatever. So I am not looking into those things, right? I'm more looking into a scientific. That means a coherence, right? The way you approach the problem has to make sense, and they follow some kind of logical argument, right? Even though you may not actually, because here we don't actually know what is the best model, right? Nobody knows it, okay? And sometimes trying to put too much belief that certain model is the best, I think you always have to be careful with that, because your training set, right? The future data that actually comes may actually be somewhat different from your training set. It all depends whether your training set is sufficiently representative of what is not seen outside, and whether things actually in the future will change, right? So that whatever conclusion that you make from your model may also actually be somewhat inaccurate. So that's why it's very important that whatever model you build, right? Sometimes you have to be a little bit, don't get too much excited that your model has some very outstanding metric or whatever. The only thing that matters is when it's deployed against the real situation and it actually has some kind of good performance against in that situation, right? So which we don't know. And sometimes actually models that are not the so-called best one, okay, but maybe the number 2 or number 3, they may actually work better in the relatively better in the new cases simply because they didn't overfit the data, right? They still captured some of the essence of the patterns in the data, but since they were not number 1, so they didn't overfit, right? So when they don't overfit, then they might actually be in a better position to do better in the next round. Okay, so that's why this area has how to use this actually properly. It requires a lot of art. Okay, the usage of the model that are optimal in some sense is only one aspect, but I think the more important part that distinguishes someone who is a skillful user of this kind of model is that the person knows the domain knowledge. The person has some domain knowledge expertise, right, to judge the models. Okay, because sometimes you can build a model that looks very nice, but the predictors that go in actually may not actually make a lot of sense, first thing. And second thing is that they may actually include a lot of predictors that are very expensive to obtain. All right, and that may not be actually very good for future usage. And sometimes it may also include some kind of variables that they are not very reliable, right, in practice. Okay, so yeah, a lot of these things, it needs a lot of practice and real experience in order to make correct judgment, right? So it's not completely a 100% math or science thing, but it has some elements of judgment involved, right, for everyone. It's just like, traders, right? People who trade stocks and all that, they all studied financial mathematics, okay? They all studied almost the same thing, but why are some stock traders more successful, right? So they definitely, but of course they will not share what they know, right? Because it's all, everyone is just keeping that as a secret, right? But yeah, you'll see that those that are more successful, either sometimes they're just lucky, right? There's no particular explanation. They just happen to make some guess that turn out correctly. But sometimes it's also dependent on the way they build their prediction models, okay? And they all learn the same math methods and all that. But if everyone is doing the same thing, then they should be performing about the same, right? But definitely that's not the case. You find that some people, they have some better intuitive understanding, and I think a lot of it comes from the fact that they actually know the subject matter. They can incorporate very subtle information from the subject matter aspect. That distinguishes them from the people who are just applying models and not considering the nature of the variables into taking that into account. Okay, so it's also something like this. Okay, but of course we are not going into that direction. As long as you can give a convincing presentation, I am fine with that. Okay. Okay, so any more questions? Yeah, that's right, Hin Chun. So you can yeah, so you can look at correlation between two variables. But interaction means that actually if you take that into consideration, it may actually it may actually kind of like after that is taken into account, the original relationship that you thought existed there may actually disappear, right? So actually a lot of the variables that are collected, they all interact with each other. So that's why it's actually not so straightforward to deploy just a multiple variable logistic regression model, because how are you going to consider what kind of interactions to put in? Usually people just dump all the possible interactions, all the possible pairwise interactions, but you know that will increase quadratically, right? If you have got n predictors, the number of pairwise interactions that you can construct is n times n minus 1 divided by 2. That's about almost like n squared divided by 2, okay? So if your n is 10, you will have about additional 50 variables for interaction terms. So one of the things that is interesting about guide is that it can actually fit different models for different partitions of the data, and I find that very powerful. And it's not very widely used by people, okay, but I think it's more of an issue about awareness rather than what the method can actually do, okay? So I think it is actually a good idea to try to run guide and see what happens, okay? Is it possible to plot the multiple variables in a two-dimensional plot? You can actually, because you can. It's always some kind of a partition, right? So it is actually possible to plot a sequence of pairwise scatter plots to indicate the how the tree actually goes through the entire thing. Okay. In this case, you are not doing logistic regression tree, right? You are doing classification. Okay. So you're just using the classification tree, using the classification tree option in guide. You can actually look at the model. Sorry, the guide manual has some examples, I think. I think maybe something like this. So for example, I just, let's say here, I have some splits like this, okay? Maybe call this x1. Sorry, maybe that's a node number, right? So let me see. Okay. So this is node 1, this is node 2. And for example, this one, let's say it's below 10, this is more than 10. And this one is some other variable, let's say x. It need not be x2, right? It could be something else, okay? 5, more than 5. Okay, so this one you classify as 1. So you classify as 1, classify as 0. This one maybe you classify as 1. Okay, so the kind of figure that it would correspond to would be like this. So first you have x. Okay, maybe let's say this is x3. Maybe this one is x1. This is x2, right? Let's see, draw. Okay, so let's see. Suppose you have something like this. Okay, so here, of course, if you make a split here, this is 10, right? So you will make a, sorry, okay, maybe let me just erase this. Okay, so if you make a split like the red line here, right? So these are mostly, so this group, so let's say this white, this empty one is 1, the filled one is 0, right? So this classification will be actually quite nice, all right? So anything 10 or below, you already classify as 1. Now you look at x2, right? x2 on x2 variable, it, you know, there's no separation that is nice, right? Because you look at x2, the empty one and the filled one, they actually stack together, right? So x2 actually is a useless variable for, it's not important for explaining the variation between these two classes. But let's see over here, this partition, right? This partition, it can go to somewhere else. So this partition, so suppose, so here I have x1, right? Okay. So this is x1 and this is x3, right? So these guys here, they are still, okay, like this, but you may find that these guys, though, the ones that are not filled here, they actually, on x3, they actually here. Okay. On x3, they actually, okay, maybe I put some of them here. Doesn't matter. They can mix together, right? But on x3, they actually, although their x1 values are here, but their x3 values are over here. And those that are the filled ones are here. So this would be very nice, right? You no longer have to consider these guys because you have already given them labels, okay? So over here, your splitting will be here, right? So anything that is less than or equals to 5, right? These guys you classify as 0, right? Above 5 you classify as 1, okay? Right, so I think the sequence of scatter plots that you are thinking about in Chun, right, is something like this, okay? But basically, whatever that's here, right, is already captured by this tree model. So this part is basically just like for your own understanding. I think this part already sufficiently captures what is actually going on here. Although it is actually nice to supplement this scatter plots to have some idea, right? Okay. So that's why it's nice, because the partitioning, right? When you have a tree structure, it basically just looks at certain partitions of the data, and at those partitions, the kind of that you might be able to find a decision rule that maximizes the separation between two different classes. Okay. Rather than looking at it globally. Looking at it globally, you will find it very difficult to find any kind of rule that will give you a very clean partition. Okay. In fact, yeah, sure. It's always good to verify it. Okay. In fact, this tree thing, right, is actually very powerful. Let me show you something. If you have, okay, just for simplicity, if you have data that looks like this, so this is known as the Mickey Mouse data, right? The Mickey Mouse data. This is like Mickey Mouse. Okay, so you have basically two types of classes, right? Plus and the circle, right? If you use a decision tree, you can actually have a partition that is separating all these these groups of data very cleanly. The first partition you might actually cut somewhere around here. Let's say this is A. Right? After you cut here, right? Then you cut here. Okay. So here, this may correspond to maybe B, right? So your model will be like this. First, your X1, anything below or equals to A, you classify as this. If your X is larger than A, right? So you consider this part here. And then you split on X2, right? So anything that is X2 less than or below B, you will classify as the plus. And anything larger than B, you will classify as circle. Okay? In fact, it also works for some very weird kind of data, like if a bunch of plus here being surrounded by a whole bunch of other variables, like other values like this. Okay, if you want to use any linear lines like one shot, right, it doesn't work. Of course, you can actually have a decision rule that is circular like this, right? Anything below and in this circle, you will classify as plus. That is what we call a support vector machine. Support vector machine with non-linear kernels. So you can actually construct this decision rule and classify it very accurately. The other way is to use the tree. So to use the tree, you would first cut. Sorry. You would first cut like this. Wait. You cut like this, right? Anything that is towards the left, you classify as minus. Then you cut this part, okay? Anything that is greater above this value, you classify as negative. And then over here, you cut, sorry, you make another cut here. Anything that is greater than or equals to this line, you classify as minus. And then finally, this one. Okay, anything that is below this line, you classify as minus. So whatever that is left is actually the plus. Okay, so then the model will correspond to one. The model will have some nodes like this. One, okay. So this first split here, and then the second node is this split, right? Then the third node is this split, okay? Anything then this. And the fourth node is here. All right, so okay, it's actually quite easy to understand. All right, and of course, the more variables that you have, basically, it is just switching between the planes. Okay, it's just moving through different planes and then making the cuts there. So actually, I think intuitively, this may be actually, it actually gives you a lot of way to visualize how the model is actually acting. Rather than if you use some other more abstract models, you may not be, you know, it's just a whole bunch of numbers coming out and you don't really know, you don't know much what is the geometry of the method. Okay, knowing how the geometry of the method works in classification is very reassuring. Okay, because it allows you to explain your method. You understand the method, and then when you understand it, then you have more confidence to explain it. Okay. Right. Okay. So I think that should be enough for the time being, right? Okay. So I'll stop the recording now, and you can send me questions through Vlog. Okay.